Okay then, good afternoon once again. So, as I said, if you haven't collected your coursework yet, you can see me afterwards. I've got the remaining ones uncollected here. So, reminder of where we were. Okay, so this is quite familiar. Did it an hour or two ago. We're solving differential equations using the Laplace transform method. We've seen a couple of examples of it now. And it involves these 4 steps: transforming the whole equation, making use of the linearity principle, the transform of derivatives property, maybe appealing to the table of transforms in order to find the transform of the right-hand side function g of t from your ODE. Second step, bringing in any of the initial values that you were provided with. Okay, so these are the constants that appear in the solution to differential equation. Remember, differential equations just on their own typically don't have unique solutions. They're normally various constants of integration that are present in the most general type of solution. Step 3, having transformed the equation, we now have an algebraic type of equation featuring functions in the new variable s. It will still feature an unknown quantity, y bar, the transform of the unknown quantity y. But this is now solvable using straightforward algebraic manipulation. Okay, just kind of reorganize the equation to make y bar the subject of the equation. And that will tell you what y bar is as a function of s, typically as a rational function of s, a quotient of polynomials. Then there's just one remaining step. Having found y bar, you then need to take its inverse transform to recover the solution y of t to the original ODE. But this is complicated by the fact that if we only have the table of transforms at our disposal, we may need to work on the form of y bar first in order to find what its inverse transform is. Typically, that will mean doing some kind of partial fraction expansion on the rational function that comes out of that solution process to find it as a linear combination of simpler types of rational function, which we can find on the table of Laplace transforms, and so recover the original solution. Also, when you look in the table of Laplace transforms, you look at the entries in it, you notice that the rational functions are presented in certain kinds of standard way. For instance, so there's 2 types of quadratic, those with an s term and those without. Those without the s term are presented up here in the middle of the table, the s squared plus omega squared, so there's no s term in that quadratic there. Okay, we've got squares of those as well. And then the quadratic polynomials which do have an s term, they are located in the bottom third of the table here. See these various denominators. But the quadratic polynomial is presented in this way as a square of a linear term, s plus a, plus or minus some constant. So it's kind of the way of presenting the quadratic as completing the square. That bit looks like the square, the bit on the left, and then you complete it by adjusting the constant to make it equal to whatever it is. So before we look at our next example of solving an ODE, we can just look at this little section here dealing with irreducible quadratic factors. So sometimes before we do that 4th step, we may need to organize things slightly so you can read it off the table, read the inverse transform off the table. So there's a little worked example here. Supposing at the end of a solution process for an ODE, suppose we end up with this expression here for y bar in equation 234. So it's a rational function, perfectly good rational function in S. It's a order 1 polynomial in S in the numerator divided by a quadratic polynomial. Okay, so functions with a quadratic in the denominator, they are on the table, in the bottom third of the table, but they're in the form where the polynomial is presented as a completion of the square. So we'd have to reorganize our denominator polynomial along those lines. So to express this as a square, well, it's obviously going to be s plus something, and the constant you use here, its purpose is to generate the 4s, so that has to be a 2. So you got s plus 2, all of it squared. So that arranges the s squared and the 4s, but then that gives you a plus 4. It's not what we want. We want a 13, so you have to add on a 9 to compensate. So changing that quadratic to s the square of s plus 2 plus 9. We rewrite the 9 as a square of 3, because in the table that's how it's presented. It's normally that constant is presented as the square of omega. So we identify the correct omega expression there as 3. Okay, so then you've got the numerator as 3s plus 18. But when you look at the table, just to bounce to the table for a second. When you look at the table, what are the numerators that go with these kinds of quadratic denominators? Well, you notice that they're either a constant, in which case the constant is omega, the square root of that constant term down there, or the numerator is s plus a, which is exactly the s plus a which is squared in the denominator. So you have to rearrange your function that you're looking at into some combination of these. And that's what is done there. So this 3s plus 18, we have to express it as a combination of s plus 2s and 3s. Okay. Well, you take the 3 out, it's going to be 3 times s plus 6. But to partner the s, we just want to have a 2. We've got s plus 2 to partner with this. And so that leaves us with a 6 here in this numerator, 3s plus 6, but we want it to be 18, so we needed a further 12. So the extra 12 is located here, but we express it as 4 times 3. Because the bit where you've got a constant here, that constant has to match the square root of the constant in the denominator. So we end up expressing our y bar as a linear combination of these two rational functions here. This one is of the form s plus a over s plus a squared plus omega squared. That is on the table. As is this one, omega over s plus something squared plus the square of omega. That's on the table as well. So we're then placed to read off, take the inverse transform of that, and to read off the solution. Okay. Using the linearity principle, it's going to be 3 times the inverse transform of this first one, plus 4 times the inverse transform of the second. Yeah. And reading off the table, we got 3 times this exponential e to the minus 2t times cosine of 3t, and then 4 times e to the minus 2t times sine of 3t. So in the course of solving your ODEs, you may have to go through a procedure like that before the final inversion of the Laplace transform. Okay, so we're going to do another example now, but before we do, any requests for clarification or questions you might have? Okay, good. So if you look over the page, the next example we encounter in the notes is, okay, we mix it up a bit. We've seen how to solve a single equation. So the next natural thing to ask would be, well, what about a set of 2 or more differential equations? So these arise quite often in applications in engineering or physics. So we got more than one unknown quantity. So here we got a pair of equations. So there's 2 unknown quantities, x and y. And it's not that we have one differential equation governing the x and another one governing the y, and then you just solve them each individually. It's not like that. This is a so-called coupled system of ODEs. Coupling means the 2 ODEs are linked in that there are 2 unknown quantities which feature in both of the equations. Okay? So you haven't just got one equation in x and one equation in y. You got 2 equations and they're both in x and y. They're both differential equations in x and y. Both of the equations feature x's and y's and their derivatives, although in the second equation it just features x. There isn't actually a further derivative of x around. But in the first equation, you've got x, a derivative of x, and a derivative of y. Okay? It's called a coupled system of ODEs. Again, it's presented to us together with some other bits of information. We've got the initial values of the two unknown functions, x of 0 and y of 0. Both of the equations are first order, meaning that the highest derivative you see around the place is an order 1 derivative. They're both linear. We don't have different derivatives multiplied together or raised to any power. So the functions are linear. They've got easily understood functions on the right-hand side, namely a constant or a multiple of t. You can take those transforms. No bother. So there's nothing else really that we need to be able to solve this. We can apply the very same process that we applied to single ODE to this pair of coupled ODEs. Okay? So there's two things we're hunting for here. We're hunting for the function x of t and the function y of t. So let's have a look at this. So again, as I go through it, as I go through the various steps, please do stop me at any time to get clarification on anything, or just as likely to point out little mistakes I make. Try not to, but we should all be alive to this and work through it together. So using slightly simpler notation for derivatives, the system is, so we'll just use this other way of writing derivatives. So the system is x prime, the first derivative of x plus the first derivative of y plus 4y prime plus 5x equals 3. And the second equation is y prime plus 3x plus y equals 2t. And this is subject to the initial conditions that x of 0 is 2, sorry, x of 0 is minus 3, and y of 0 is 2. Okay, those are the initial conditions. Okay, so we can go through the solution of this. First step, just as in the previous examples, is to transform both equations. Okay, this time we've got two equations. Transform them both. In the course of doing that, use the linearity property and the transform of derivatives property. Okay, transform both equations using, I won't spell out every individual application out, I'll just say using linearity and the transform of derivatives property. Okay, using linearity and the transform of derivatives properties. Okay, x and y are unknown to me, so I'm going to refer to the transform of x as x bar and the transform of y as y bar. So x bar is going to represent the transform of x. Y bar, the transform of y. Agreed? So using the transform of derivatives property, the transform of the first derivative is s times x bar minus x of 0. The transform of 4 times y, 4 times the derivative of y, that's going to be 4 times s times y bar minus 4 times the initial value of y. And then I've got plus 5 times x bar. And then I've got the transform of 3, which is 3 over s. The second equation, transform of the derivative of y is s y bar minus the initial value of y. Transform of 3x is 3 times x bar. And the transform of y is y bar. And this is equal to the transform of 2t, which is 2 over s squared. Okay, so using standard transforms, transform of constant, transform of multiple of t. Transform of derivatives property to generate terms like this and this here, and this one here, 4 times this one. and then writing x bar and y bar for the transforms of x and y themselves. So that's the end of that step, transforming both equations. Next is to bring in the constant values that we were provided with, the initial values of x and y. Bring in the values for x of 0 and y of 0. Let's just write it out. X bar, x of 0 is minus 3, so this is plus 3. It's 4s, y bar, minus 4 times y of 0, so it's going to be minus 8. Then plus 5x bar is 3 over s. And the second one, I've got s times y bar minus 2. So no others, plus 3x bar plus y bar, and still equal to 2 over square of s. Yeah, I probably could have combined that with the next step, but it didn't happen. So this is now a pair. So the structure is simplified quite a lot. I've still got two unknowns, x bar and y bar, but it's now just kind of an algebraic type equation. There's no more derivatives around, just x bar and y bar, maybe slightly complicated by multiplying them by that new variable s. Okay. So now the thing would just be to simplify these equations by collecting together the x bar and the y bar in both equations. So in the first one, multiplying x bar, I've got s plus 5. Okay, so you just got to make your s's and 5's nice and distinct from each other. S plus 5 times x bar. And multiplying y bar there, you've just got 4s. This is equal to, now we've also got constants here. We've got a 3 and a minus 8. So that's a minus 5. You bring it over the other side, it's a plus 5. And I'll put it over s, just have a single fraction here. So it's going to be 3 plus 5s squared. Right? No, 3 plus 5s. So 3 minus 8 there becomes a minus 5 here. To go over the other side, it's a plus 5. To bring it, I just want to see a single fraction here just for simplicity. So I'm making 5s over s. Okay, that's the first equation. Then the second equation, similarly. So what x bars do we have? We just have 3x bar. And what y bars do we have? We've got s plus 1. And then it's constant minus 2, so it becomes a plus 2. We've got s squared, 2 plus 2s squared. And I'll put a box around that. So that's my pair of transformed equations tidied up. Yeah. So we've got x bar and y bar on the left-hand side, rational function of s on the right-hand side. The equations are still coupled. X bar and y bar are involved in both. But we can now set about solving these algebraically. Maybe you might want to label them here, just so I can refer to them. So I'll call them A and B. So these are the simplified transformed equations. Simplified or tidied up transformed equations. So we can now proceed to start solving them by eliminating one of the variables. Okay, just using that very familiar process of variable elimination. These are the simplified transformed equations. You start to solve them by eliminating one of the variables. Variables being x bar and y bar. So which one is going to get the chop? my notes here of eliminate x bar. So what I want to do is use both the equations to produce a new equation, but which doesn't have an x bar in it. So when you look at the coefficients of x bar, you've got s plus 5 and 3. So the only way we're going to cancel those out is if I take 3 times the first one and minus s plus 5 times the second one, I guess. And avoiding fractions, I'll just multiply by the integers as appropriate. So if I consider the equation 3 times a minus s plus 5 times b, that will get rid of the x bar, won't it? The coefficient of x bar in 3a is the same as the coefficient of x bar in s plus 5b, and then you subtract them, so they disappear. So the x bars disappear, but we will still have y bars. So let's just write it out. Okay, so this is where the algebra can get a little bit involved. Just give myself room, I'll just come down here. So we've got 12s y bar. That's the y bar in 3a. The y bar in s plus 5b is s plus 5 times s plus 1 y bar. Minus s plus 5 s plus 1 y bar. So that's the left-hand side. Then looking at the right-hand side, okay, the right-hand side of 3a, so 3 times all of that, it's not too bad. 9 plus 15s. Again, what's your s's and 5s? 9 plus 15s over s. And then I have to subtract s plus 5 times that. Which, yeah, I just do. Minus s plus 5 times all of this, which is 2. It's 2s squared over s. So success in the terms of there's no x bar anymore. Just a single equation involving y bar. And it's not that complicated. It's just a polynomial in s times y bar plus another polynomial in s times y bar equals a rational function in s. So we can just make y bar the subject of this. So we reorganize this. To find y bar. So how might we do that? Well, on the left-hand side, multiplying y bar, we've just got quadratic. And that quadratic is minus, well, it's a minus s squared. So if I take a minus out of everything, it's s squared. And then how many s's we got? Minus 6x y bar plus 12. So in total it's minus 6. But from taking the minus sign out, it's going to be plus 6. Yeah, so it's going to be minus 6s. And then constant, I've got minus 5. But I've already taken the minus sign out. That's plus 5. So let's multiply y bar, the left-hand side. And on the right-hand side, well, I've got something over s plus something over s squared. So just to keep things ticking along, let's put it all over s squared. Shouldn't be too hard. So what's going on with this? This is going to be a polynomial. Now, if you look, the highest degree term you have around is an s cubed. This is 2s squared times an s. So that's going to be an s cubed. And there's a minus sign, so it's going to be minus 2s cubed. looking for s squareds. There's minus 10 s squared there. And then you also get 15s squared there, because the 15s is over s, so you got to multiply above and below by s to bring it over s squared. So the minus 10s squared from the right hand gets with the plus 15s squared, so it should be plus 5s squared. 2, I believe. Then you're looking for s's. We got 9s there. Remember, it's 9 over s, but then you've got to multiply above and below by s to get s squared on the bottom. You got 9s there, and here, how many s's? You've got minus 2s. So 9s minus 2s is a plus 7s. Constant term is just minus 10. You just have a minus 10 from here. 5 times 2, 10, minus 10. And there's no constant term here. Got to multiply above and below by s then, so that's just minus 10. Okay, so now we can make y bar the subject of this. Dividing both sides by s minus s squared minus 6s plus 5. So in the bottom here, I'll have s squared multiplied by s squared minus 6s plus 5. And dividing by that minus sign just flips all those minus signs. So 2s cubed minus 5s squared minus 7s plus 10.
I think there's only 3s squared.
3s squared instead of 5.
You've got a minus 10 when you're expanding the bracket, and a minus 2.
How many s squareds? So the way you get s squared, here. The way you get s squareds here is by multiplying the 5 by the 2s squared. Yeah? So that gives you minus 10.
I think it might be.
Okay. I think this is okay, because I'm agreeing with my notes so far, and I did recalculate it.
Isn't that minus 6s plus 6s in the brackets? Because it's a minus overall.
Sorry, which bit?
That minus 6s in the brackets.
Here.
Yeah, isn't that supposed to be plus? Because it's minus overall.
Well, let's look at what we have here. So it's multiples of s times y bar. I've got 12s here. Here I've got minus 6s. So it's 12s minus 6s. So it's plus 6s overall. But because I brought out that minus sign, then it's a minus inside. Yeah. It just shows you it's quite tricky when you got minus signs. You got different fractions. You're pulling fractions together, pulling them apart. You just got to proceed carefully. Okay. So there's our solved equation. We'll solve for one of the variables anyway. There's our y bar. So in principle now, all we have to do is just take the inverse transform. But of course, you look at the table of transforms, there's nothing that looks exactly like that. We got to embark on our partial fractions rewriting of it. The linear combination of simpler rational functions which we can find on the table. Okay. So first of all, now you've been staring at that for a while. You'll notice that that does have a nice factorization. It's s minus 5 by s minus 1 times that quadratic. But then we're still left with dealing with that cubic at the top. But before we proceed, you notice something nice about these coefficients. The 2 minus 5 minus 7 plus 10, they sum to 0. Don't they? 2 minus 5 is minus 3, minus 7 is minus 10, plus 10 is 0. So if the coefficients of the polynomial sum to 0 like that, then when you evaluate the polynomial at s equals 1, you'll get a 0. So that means s equals 1 is a root of the numerator, so s minus 1 will be a factor of it. So we can divide, we should be able to divide the numerator by s minus 1. and see what gets left behind. Just simplify it a little bit. So what gets left behind is 2s squared minus 3s minus 10. Okay, so that's after dividing by s minus 1. Okay, so we simplified it a bit, but you still can't find that in the table. Okay, so before inverting the transform, we need to find a partial fraction expansion. So the partial fraction expansion of that function. So it's a rational function in S. We've got the denominator factorized. Yeah, so y bar is going to be, what do I call these of the ABCs? It's going to be something over S plus something over S squared. Remember, when you've got one of the factors, when you've got a linear factor, S plus a constant, okay, that's S plus 0. A linear factor raised to a power. In the partial fraction expansion, you might have a constant over that factor for each increasing exponent all the way up to the one that appears there. So in that case, it's something over S plus something over S squared. And then there might be something else, a C, over the other factor, S minus 5. Okay. Then the way I normally do it is to immediately collapse that again back to this form here, over S squared times S minus 5, but this time you're tracking how the A, B, and C come through. So the A has to multiply S times S minus 5, B has to multiply S minus 5, and the C has to multiply S squared in order to put those three fractions over the common denominator, S squared times S minus 5. And then we're again looking at a quadratic polynomial there in the numerator, which needs to be compared, to the original one there. And we want to determine A, B, and C. So what quadratic factors do we have? We've got an A times S squared plus a C. So it's A plus C times S squared. What S's do we have? We've got minus 5A plus B times S. And then what constants do we have? We just have minus 5B. So I put that numerator polynomial back into standard form, something times S squared, something times S, constant. Now I can compare it back to the original one here. So I'll label this, have I labeled anything here? A, yeah. Over C, over D. So C and D are two fraction expressions, both of them over S squared, S minus 5. So the numerators must be equal. They're both equal to Y bar. So comparing numerators, C and D, we find, well, okay, the numerators are polynomials in S. How can these two polynomials in S be equal? The only way you can have different polynomial functions being equal as functions all the time, not just intersecting and some kind of simultaneous solution, but being actually equal, is if the coefficients of corresponding powers of S are the same. So this constant coefficient here, minus 5b, must be equal to the constant coefficient up there, minus 10. Coefficient of S here, this minus 5a plus b, must equal the coefficient of S up there, which is minus 3. And the S squared coefficient, a plus c, must equal the S squared coefficient up there, which is 2. So what you get typically out of this is a system of linear equations in your unknown constants from the partial fraction expansion. System of linear equations, you can always solve by row reduction, by Gaussian elimination. That's not really necessary here because one of them is already in the form of a solution. That can only be true if b is 2. If b is 2, becomes a minus 2, so minus 5a equals minus 5, so a must be 1. And if a is 1, then c is 1. So the solution drops out. It's in effect, it's already a kind of reduced system. Somewhat. Cool. So that agrees with what I had before. Almost a good sign. So y bar now I've got these values. Y bar is a over s, so 1 over s, plus b over s squared, 2 over s squared, plus c, which is 1 over s minus 5. That's our y bar. Now, in this much nicer expression, linear combination of simple enough rational functions, each of which can be found on the table of Laplace transforms. So the solution for y is y of t, the inverse transform of y bar, the inverse transform of all of this, which is constant 1 plus 2t plus e to the 5t. Excuse me. Not so fast though. That's really just half the solution. Remember, it was a pair of coupled ODEs at the beginning in x and y, so that's half of the solution. So half the solution to the original system. So we now need to go back and somehow get the solution for x. There's a few different options here. In principle here, what you kind of have to do is go back to your transformed equations, take the solution for y bar that you have, put it into those, you get an equation for x bar, solve for x bar, and inverse transform. Okay? So in principle, we can return to equations A or B. A and B were the two transformed equations. Return to those with our solution for y bar. Solve for x bar, then invert the transform to get x of t, and you're done. That will be the final solution obtained. That's in principle what we have to do. In this particular example, we can save ourselves some work because one of the original ODEs was particularly nice, okay? Here we can shortcut this slightly without the need for doing more solution in terms of s and partial fraction expansions. We can shortcut this a bit by examining the second ODE. Because the second ODE looks a lot simpler now, given that we've got y. So that was the second ODE, the derivative of y plus 3x plus y plus 2t. We've already found the solution for y. It's 1 plus 2t plus e to the 5t. Trivial enough to differentiate y, to obtain y bars, to obtain the derivative, y prime. So we can just substitute y and y prime into here and divide everything by 3 and we'll get x, the solution for x. So the derivative of y is 2 plus 5 e to the 5t. 3 times x plus 1 plus 2t plus e to the 5t is supposed to be equal to 2t. And we can pretty quickly solve that for x. X, which is a function of t, after all. And so what's going on here? Constants, there's a 2 here, and a 1, that's a 3, move across into minus 3. There's a 5e to the 5t plus e to the 5t, so it's a 6e to the 5t, moved across into minus 6e to the 5t. And there is this 2t here, but there's also a 2t there. So finally, our solution x of t seems to be minus 1 minus 2e to the 5t. Pretty good. So that's the second half of our solution. Okay, so that example shows that not only can we cope with single ODEs, in principle, within reason, we can also cope with systems of ODEs. Just transforming the system, you get a new system, kind of an algebraic system in the same number of unknown quantities, which you can solve algebraically, eliminate variables as you go, solve for the new unknown variables, and at the end of the day, take inverse transforms and recover the original solution. Okay, thanks for listening. I'll see you yet again in a couple of hours, 4 o'clock. Finish the marathon.